Sequoia National Park. National Parks of the United States. To understand the magnitude of Sequoia National Park, one must first dismantle the human concept of scale. In the modern world, we measure greatness in height, in volume, or in the speed of transmission. But in the southern Sierra Nevada mountains of California, greatness is measured in biological endurance and geological audacity. This is a landscape where time moves at the pace of shifting tectonic plates and the slow, hydraulic lift of sap rising through ancient xylem. Sequoia National Park is not merely a collection of trees, it is a complex, vertical sanctuary that encompasses nearly every ecological zone present in the North American continent, compressed into a steep, rugged gradient of granite and chlorophyll. Established on September 25, 1890, it holds the distinction of being the second national park created in the United States, following only Yellowstone. It was born out of a desire to protect the giant sequoia trees from the ravages of industrial logging, a movement spearheaded by conservationists who recognized that these organisms were not merely timber, but living monuments of a past geological epoch. Located in the southern section of the Sierra Nevada range, east of the San Joaquin Valley, the park spans over 400,000 acres, but its footprint on the scientific understanding of botany, fire ecology, and geology is far larger. The identity of the park is dualistic. To the casual observer, it is the land of the giants, the home of the Sequoiadendron giganteum, the most massive trees on Earth. However, the scientific reality is that the giant sequoias are the crown jewels of a much broader, more intricate geological and hydrological kingdom. The park is a realm of extremes, rising from the dry, sun-baked foothills at roughly 1,300 feet above sea level to the jagged, oxygen-thin summit of Mount Whitney, which at 14,494 feet is the highest point in the contiguous United States. This dramatic vertical relief, occurring over a relatively short horizontal distance, creates a compressed layering of climates and habitats. A traveler moving from the Ash Mountain entrance to the high Sierra crest traverses the ecological equivalent of a journey from Mexico to the Arctic Circle, passing through chaparral, oak woodlands, mixed conifer forests, subalpine belts, and finally, the stark, glaciated alpine zone. The geological foundations of Sequoia National Park tell a story of fire and ice, forces that seem contradictory but worked in tandem to sculpt the scenery we witness today. The backbone of the park is the Sierra Nevada batholith. A batholith is a massive intrusion of igneous rock, formed deep beneath the surface of the Earth. During the Mesozoic era, roughly 100 million years ago, the subduction of the Farallon tectonic plate beneath the North American plate generated immense heat and pressure. This process melted the rock of the continental crust and the subducting plate, creating large chambers of magma. This molten rock did not erupt as volcanoes, but instead cooled slowly underground, crystallizing into the hard, speckled rock we know as granite. Over millions of years, the overlying sedimentary and metamorphic rocks eroded away, revealing the granite core. Then, through a process of crustal extension and faulting, this massive block of granite was tilted upward, steeper on the eastern side and gentler on the western slope. This tilting action created the Sierra Nevada range. As the granite was exposed to the lower pressures of the surface, it began to expand. This expansion caused the rock to fracture in parallel layers, a process known as exfoliation. This geological phenomenon is responsible for the distinct dome shapes seen throughout the park, most notably Morro Rock. Morro Rock is a granite dome that offers a panoramic view of the Great Western Divide, and its shape is the direct result of these onion-like layers of rock peeling away over millennia. While the uplift created the canvas, it was the ice ages of the Pleistocene epoch that painted the details. Massive glaciers, rivers of ice, thousands of feet thick, flowed down the V-shaped river valleys, scouring the bedrock and widening the canyons into the characteristic U-shapes seen in Toccopa Valley and the canyon of the Kern River. The glaciers acted as nature's bulldozers, plucking boulders from the mountainsides and depositing them miles away as glacial erratics, rocks that sit strangely on the landscape, composed of different material than the ground beneath them. The jagged peaks of the High Sierra, known as horns and arides, were sharpened by the heads of these glaciers, creating the saw-toothed horizon that defines the park's eastern boundary. Hydrology in Sequoia National Park is the lifeblood that connects the high peaks to the valley floor. The park acts as a massive water tower. During the winter months, Pacific storms collide with the Sierra Nevada range. As the moist air is forced upward, it cools and condenses, dropping massive amounts of snow on the high country. This snowpack is the primary reservoir for the ecosystem. In the spring and summer, the slow melt of this snow feeds the Sequoia, Kern, and Kings rivers. This water does not just flow over the surface. It interacts with the geology in surprising ways. While the park is famous for its granite, it also contains significant bands of marble, a metamorphic rock derived from ancient limestone. This marble is soluble in water, especially water that has picked up carbon dioxide from the soil to become a weak carbonic acid. This chemical interaction has riddled the park with karst topography, creating over 200 known caves, including the famous Crystal Cave. These subterranean landscapes are decorated with stalactites, stalagmites, and draperies, formed drop by mineral-rich drop over hundreds of thousands of years. These caves are not merely geological curiosities. They are stable environments with constant temperatures that support unique ecosystems of invertebrates and bats, creatures adapted to a world without sunlight. The vegetation of Sequoia National Park is defined by the availability of water and the temperature, both of which are functions of elevation. In the lowest elevations, the foothills, the climate is Mediterranean, hot, dry summers and mild, wet winters. Here, the landscape is dominated by blue oak savannas and chaparral. The plants here are survivors. Chamise, manzanita, and yucca have evolved mechanisms to retain moisture. The leaves of chaparral plants are often small, hard, and waxy, a modification known as sclerophyll, which reduces water loss through transpiration. The blue oak is particularly adapted to drought. In extremely dry years, it can drop its leaves entirely to go dormant, waiting for the rains to return. This zone is biologically rich, teeming with mule deer, bobcats, and rattlesnakes, but it is often overlooked by visitors rushing to see the big trees. As one ascends past the 5,000-foot mark, a profound shift occurs. The air cools and moisture becomes more abundant. This is the montane forest, the transition zone where the giants dwell. The mixed conifer forest of Sequoia National Park is arguably one of the most productive biomass generators on the planet. It is here that we find the park's namesake, the giant sequoia, or Sequoiadendron giganteum. To understand the giant sequoia, one must differentiate it from its cousin, the coast redwood, or Sequoia sempervirens. While the coast redwood grows taller, thriving in the coastal fog belt, the giant sequoia is the champion of volume. It is a tree of the mountains. These trees are remnants of a lineage that once covered much of the northern hemisphere, but today they are restricted to roughly 75 groves on the western slopes of the Sierra Nevada. The biology of a giant sequoia is a masterclass in adaptation. These trees can live for more than 3,000 years. The General Sherman tree, the largest known living single-stem tree on Earth by volume, is estimated to be between 2,300 and 2,700 years old. Its base diameter exceeds 36 feet, and it stands 275 feet tall. But how does an organism of this size function? The challenge of transporting water from the roots to the crown against the force of gravity is immense. Sequoias utilize the physics of capillary action and negative pressure generated by the evaporation of water from their needles, a process called transpiration, to pull water up the trunk like a giant straw. However, this system has physical limits, which explains why they do not grow infinitely tall. Eventually, the physics of water transport cannot overcome gravity and friction. The survival of the giant sequoia is inextricably linked to fire. For decades, early park management followed a policy of total fire suppression, believing that protecting the trees meant stopping all fires. Science has since corrected this view, revealing that Sequoiadendron giganteum is a fire-dependent species. The reproductive cycle of the sequoia relies on heat. The trees produce small, egg-sized cones that can hang on the branches, green and closed, for up to 20 years. Inside these cones are tiny seeds resembling flakes of oatmeal. For the cones to open and release these seeds, they usually require the drying heat of a fire. Furthermore, fire clears the forest floor of thick layers of duff, accumulated needles and debris that would otherwise prevent the seeds from reaching the mineral soil they need to germinate. Fire also burns away competitors like white fir and incense cedar, which would otherwise shade out the sun-loving sequoia seedlings. The bark of a mature sequoia contributes to this resilience. It can be up to 2 feet thick and is fibrous and non-resinous. It acts as a thermal insulator, protecting the living cambium layer beneath from the heat of flames. The tannins in the wood also make the tree highly resistant to rot and insect infestation. Thus, the frequent low to moderate intensity fires that historically swept through these forests were not disasters, but regenerative events. The ecological zone surrounding the sequoias includes other majestic conifers. The sugar pine, with the longest cones of any pine species, hangs its reproductive payloads from the tips of long, sweeping branches. The ponderosa pine and the Jeffrey pine, with their puzzle-piece bark that smells of vanilla or butterscotch, anchor the drier slopes. Within this forest, the interplay of species drives the ecosystem. The Douglas squirrel, or chicory, is a hyperactive engineer of the woods. These squirrels harvest sequoia cones by the thousands, gnawing through the fleshy scales to get to the seeds. In doing so, they often drop seeds or berry cones that they never retrieve, acting as agents of dispersal. The interactions continue into the soil. The roots of these conifers are symbiotic with mycorrhizal fungi. The fungi attach to the tree roots, extending the root system's reach and breaking down nutrients in the soil in exchange for sugars produced by the tree's photosynthesis. This underground network connects the forest in a way that is invisible to the naked eye, but essential for the nutrient cycling of the park. Climbing higher still, the forest begins to thin. We enter the subalpine zone, a landscape of stark beauty and harsh conditions. Here, the growing season is short, lasting only a few months. The trees that survive here, such as the foxtail pine and the whitebark pine, are sculpted by the elements. The foxtail pine is endemic to California, found only in the Klamath Mountains and the Southern Sierra. Its bottleneck, brush-like needles distinguish it as a survivor of the high country. Near the tree line, the limit where trees can no longer grow, the vegetation becomes stunted and twisted, a form known as Krummholz, a German word meaning, quote, crooked wood. These trees grow low to the ground, protected by the winter snowpack from the abrasive wind and ice crystals. Above the tree line lies the alpine zone, a world of granite, sky, and hardy biological endurance. This is the domain of the pika and the yellow-bellied marmot. The American pika, a small relative of the rabbit with round ears and no visible tail, lives in the talus slopes, piles of broken rock. Pikas do not hibernate. Instead, they spend the short summer frantically harvesting grasses and wildflowers, creating hay piles in the crevices of the rocks to sustain them through the long, frozen winter. They are considered an indicator species for climate change. Because they are adapted to cold temperatures, they cannot survive if their environment becomes too warm, and as temperatures rise, they are forced higher up the mountain until there is nowhere left to go. The yellow-bellied marmot, in contrast, chooses hibernation, slowing its metabolism to a crawl to sleep through the harshest months. The fauna of Sequoia National Park is as diverse as its flora, with food webs that span the elevation gradients. The apex predator of this system is the mountain lion, a stealthy hunter that regulates the population of mule deer. The interaction between predator and prey prevents the deer from overgrazing the vegetation, maintaining the structural complexity of the habitats. The American black bear is the most iconic mammal of the park. Despite their name, these bears can range in color from blonde to cinnamon to jet black. Sequoia National Park provides a critical habitat for them. Unlike the grizzly bear, which was hunted to extinction in California in the 1920s, the black bear has adapted well to the Sierra Nevada. They are omnivores, opportunistic feeders whose diet consists largely of grasses, roots, berries, and insects, with meat making up a smaller portion of their intake. In the fall, they go into a state of hyperphagia, eating nearly non-stop to build up fat reserves for winter hibernation. Their activity helps disperse seeds of berry-producing shrubs like manzanita and elderberry across the landscape. Bird life in the park is stratified by elevation. In the foothills, the acorn woodpecker creates granary trees, drilling thousands of holes in dead wood to store acorns. In the coniferous forests, the pileated woodpecker, the size of a crow with a brilliant red crest, excavates large rectangular holes in dead trees in search of carpenter ants. These cavities later provide nesting sites for owls, flying squirrels, and other cavity-nesting birds. High in the granite cliffs, the peregrine falcon, the fastest animal on Earth, hunts on the wing. And soaring on the thermals, columns of rising warm air, generated by the heating of the rock faces, one might see the golden eagle, scanning the open slopes for marmots or ground squirrels. The hydrology of the park is not limited to the rivers and caves. It also encompasses the high-altitude lakes and meadows. The meadows, such as Crescent Meadow and Log Meadow, are sponges. They are filled with sediments and organic matter that absorb the spring runoff and release it slowly throughout the summer. These wet environments are biodiversity hotspots, bursting with wildflowers like corn lilies, shooting stars, and lupines in the summer. They act as natural filtration systems, cleaning the water before it descends to the valley. The high alpine lakes, sitting in the bowls carved by glaciers called cirques, are crystalline and cold. Historically, many of these high lakes were fishless because waterfalls downstream prevented fish from migrating up. However, early stocking efforts introduced trout to many of these waters, which altered the ecosystem by predating on the native amphibians, such as the mountain yellow-legged frog. Current conservation science in the park involves removing non-native fish from certain high lakes to allow the endangered frog populations to recover. Geological processes in the park are ongoing. Rockfall is a constant and dynamic force. The same exfoliation that created the domes continues today. Water seeps into cracks in the granite, freezes at night, and expands, wedging the rock apart, a process known as frost wedging. Eventually, slabs of rock, sometimes the size of buildings, detach and thunder down the canyon walls. This is not a sign of instability, but a natural method of mountain shaping. It keeps the canyon walls steep and refreshes the talus slopes at the base. creating new habitats for the pikas and lizards. The atmosphere itself is a component of the park's natural foundation. The air quality in Sequoia National Park is the subject of complex scientific study. While the high Sierra air is generally pristine, the geography of the range traps pollutants drifting from the agricultural and industrial activities in the San Joaquin Valley below. Ozone and particulate matter can be pushed up the slopes during the day by thermal updrafts. This affects not only human health but the physiology of the plants. Ozone damage can be seen on the needles of the Jeffrey pines, causing chlorotic mottling, yellow spots where the plant tissue has died. This weakens the trees, making them more susceptible to bark beetles and drought. This atmospheric connection highlights that even a protected wilderness is not isolated from the anthropogenic influences of the surrounding region. The concept of the critical zone is useful when discussing Sequoia National Park. Scientists define the critical zone as the thin veneer of Earth's surface, from the top of the tree canopy to the bottom of the groundwater aquifers. In Sequoia, this zone is deep and complex. The giant sequoias interact with the atmosphere hundreds of feet in the air, capturing carbon and intercepting fog. Their roots interact with the deep soil and the regolith, the layer of loose, heterogeneous, superficial deposits covering solid rock. The granite bedrock, though seemingly solid, is fractured and holds deep reservoirs of water that trees can tap into during severe droughts. Isotope analysis of water in tree xylem has shown that during the driest years, trees switch their water source from surface soil moisture to deep rock moisture, highlighting the unseen connections between geology and biology. One of the most distinctive natural features of the park is the Kern Canyon. Unlike most major Sierra canyons that run perpendicular to the range axis, west to east, the Kern River follows a fault line that runs north to south for many miles before turning west. This structural control creates a remarkably straight and deep trench, almost 3,000 feet deep in places. This geography isolated the native rainbow trout in the Upper Kern Basin for thousands of years, leading to the evolution of a distinct subspecies, the California golden trout. This fish, with its brilliant gold sides and red sash, is the state fish of California and is found natively only in the Kern River drainage of the southern Sierra. Its existence is a testament to how landscape features like faults and glaciers can isolate populations and drive evolutionary divergence. The fire regime of the park is undergoing a significant transition due to climate change. Historically, the mixed conifer forest experienced frequent, low-intensity surface fires. However, a century of fire suppression allowed vegetation density to increase dramatically. Combined with hotter, drier summers and longer fire seasons, this has led to a shift toward high-severity fires that can reach the canopy of the giant sequoias. While mature sequoias are adapted to fire, they are not immune to the extreme heat generated by these fuel-loaded megafires. In recent years, fires like the Castle Fire have killed varying percentages of the mature giant sequoia population. This has sparked an urgent scientific and management response, involving manual thinning of the forest and the careful application of prescribed burns. Intentional fires set by managers under specific weather conditions to reduce the fuel load and mimic the natural disturbance cycle that the trees depend on. The specific groves of the park each have a unique character shaped by their topography. The giant forest, home to the General Sherman tree, sits on a rolling plateau. This relatively flat terrain at high elevation helps retain soil moisture, allowing for a high density of massive trees. It is a cathedral-like environment where the canopy is so high that the ground layer remains in a perpetual dappled twilight. In contrast, the Muir Grove is more remote, requiring a hike to access, offering a sense of solitude that reflects the primeval nature of the forest. The Grant Grove, actually located in the adjacent Kings Canyon National Park, but ecologically contiguous and managed jointly, protects the General Grant tree. These groves are often separated by deep canyons or ridges where the soil is too thin or the exposure too great for the giants to thrive, creating an island-like distribution of the species. The interactions between the biological and physical worlds in Sequoia are nowhere more evident than in the carbon cycle. The forests of the park are massive carbon sinks. A single giant sequoia holds a staggering amount of carbon in its trunk, branches, and roots. Because the wood is rot-resistant, even when a sequoia falls, it releases that carbon back into the atmosphere very slowly, sometimes over centuries. The downed logs become nurse logs, providing a nutrient-rich, moisture-holding seedbed for the next generation of trees and habitat for insects and fungi. This slow decomposition creates a carbon pool that is much more stable than that of forests dominated by faster rotting species. In the high country, the absence of trees reveals the raw geology of the Sierra Nevada. Mount Whitney and its surrounding peaks are composed of granite that intruded the crust about 80 million years ago. But looking closely at the peaks, one might see darker rocks sitting on top of the light gray granite. These are roof pendants, remnants of the ancient metamorphic rock that once covered the batholith before erosion stripped it away. They are the roof of the magma chamber that didn't quite erode completely. These rocks tell the story of the land before the granite arrived, a time when this area was a shallow sea. The fossils found in these metamorphic remnants provide the timeline for the geologic uplift. The water that flows from the melting snow of the High Sierra is ultra-pure, having very low dissolved solids. This purity is due to the insolubility of the granite bedrock. Unlike limestone or sandstone, which dissolve easily, granite is resistant to chemical weathering. This results in the gin-clear water characteristic of Sierra lakes. However, this low nutrient content makes the aquatic ecosystems fragile. They are oligotrophic, meaning low in biological productivity. The introduction of even small amounts of nutrients from human waste or atmospheric deposition can disrupt the balance, leading to algae blooms that threaten the clarity and chemistry of the water. The seasons in Sequoia are distinct and dictate the rhythm of life. Winter is the season of silence and accumulation. The snowpack builds, insulating the ground and the roots of the plants. The sequoias, with their flexible branches, shed the heavy snow loads that would snap the limbs of lesser trees. Spring is the season of hydraulic power. As the sun angle increases, the meltwater pulses down the creeks. Waterfalls like Tacoma Falls become thundering torrents. The dormant plants in the foothills explode into color, with California poppies, fiddlenecks, and lupines carpeting the slopes. Summer is the season of growth and stress. The water becomes scarce in the lower elevations, and the fire risk rises. The high country becomes accessible, and the wildflowers bloom in the alpine meadows. Autumn is the season of preparation. The deciduous trees, like the dogwood and the black oak, turn gold and orange. The animals rush to gather the final calories before the snow returns. The interconnectedness of Sequoia National Park's ecosystems means that a change in one variable ripples through the whole. A reduction in the snowpack due to warming temperatures affects the water availability for the sequoias in the summer. It reduces the flow in the rivers, affecting the trout. It changes the timing of the wildflower bloom, which can desynchronize the relationship between flowers and their pollinators, such as bumblebees and hummingbirds. The park is a living laboratory where these dynamics play out in real time. The study of tree rings, or dendrochronology, in the park allows scientists to reconstruct the climate history of the region for the past several thousand years. The rings of dead giant sequoias and foxtail pines record wet years as wide growth rings and drought years as narrow ones. These natural archives provide the baseline data against which modern climate trends are measured. Even the soil of Sequoia National Park is a distinct entity. In the sequoia groves, the soil is often a specific type known as a taxonomic family of soils of the Sierra Nevada. It is derived from the weathering of granitic rocks and is acidic, coarse-textured, and well-drained. This drainage is crucial. While sequoias need vast amounts of water, their roots will rot if they sit in stagnant, saturated soil. The soil ecology includes nematodes, springtails, and vast networks of fungal mycelium that physically hold the soil together, preventing erosion on the steep slopes. The protection of this soil resource is as important as the protection of the trees themselves, for without this specific substrate, the giants could not stand. The park's location on the western slope of the range means it acts as a barrier to the weather systems moving off the Pacific Ocean. This orographic lifting effect causes the park to receive significantly more precipitation than the lands to the east of the crest. This creates a rain shadow effect, leaving the Owens Valley to the east arid and desert-like. This sharp climatic divide is visible from the summit of Mount Whitney. To the west, a sea of green ridges and deep canyons. To the east, a precipitous drop into the brown, dry expanse of the Great Basin. This contrast highlights the role of the Sierra Nevada as a major climatic divide for the continent. Sequoia National Park is a place where the biological timeline overlaps with the geological timeline. A visitor standing at the base of a giant sequoia is in the presence of an organism that may have been a seedling when the Roman Empire was at its height. That same visitor is standing on rock that cooled from magma when dinosaurs roamed the earth. The air they breathe is being scrubbed by the largest leaves and needles in the world, and the water they drink is ancient snowmelt filtered through primeval stone. The park preserves not just a collection of scenic views, but a functional, albeit changing, slice of the planetary life support system. It is a testament to the power of protection, the resilience of life, and the enduring complexity of the natural world. While the geological architecture and the botanical giants provide the static framework of Sequoia National Park, the landscape is neither silent nor empty. It is a dynamic stage where human history has played out for millennia, and where complex animal societies navigate a vertical world of fluctuating resources. To fully comprehend the park, one must look past the immobility of the granite and the endurance of the trees to see the ephemeral, fluid movements of the people who shaped the ecology long before the arrival of the cavalry, and the intricate behaviors of the wildlife that continue to weave the food web together today. The history of humans in this region contradicts the early preservationist ideal of a pristine, uninhabited wilderness. Archaeological evidence indicates that the southern Sierra Nevada has been inhabited for at least several thousand years, with the primary residents at the time of European contact being the Monashi or Western Mono people. These indigenous groups were not merely transient visitors, but established sophisticated seasonal migration patterns that mirrored the behavior of the wildlife they relied upon. This lifestyle, known as vertical transhumance, involved spending the mild winters in the foothills below the snowline, where the temperatures remained moderate, and moving into the higher elevations of the conifer belts during the summer to escape the heat and harvest the ripening resources of the high country. The ecosystem that John Muir and early settlers described as quote, like and natural was, in reality, a managed landscape, tended to by the Monache and neighboring tribes like the Yokuts and Tabatulabal through selective harvesting and, most importantly, the intentional application of fire. The cultural connection to the land is physically embedded in the granite bedrock itself. Throughout the lower elevations of the park, particularly in areas like Hospital Rock and Potwisha, visitors can find bedrock mortars, smooth, deep depressions worn into the solid stone. These are the manufacturing sites of the primary staple of the indigenous diet, the acorn. The transformation of the acorn into edible food is a process requiring deep knowledge of chemistry and hydrology. Acorns from the black oak, which grows in the transition zone between the foothills and the conifer forest, were preferred for their flavor and oil content. However, raw acorns contain high concentrations of tannins, bitter compounds that are toxic in large quantities. The women of the tribes would grind the shelled acorns into a flour in these mortars, using cobblestone pestles. The flour was then placed in sand basins or basketry filters, and water, often warm water heated with hot stones, was poured over it repeatedly. This leaching process flushed away the water-soluble tannins, leaving a nutritious, nutty dough that could be cooked into a mush or baked into bread. The abundance of these mortars at specific sites suggests large, communal gatherings, indicating that the harvest season was not just an economic activity, but a central pillar of social structure and cultural transmission. Trade networks were vital to the pre-colonial economy of the region, defying the formidable barrier of the Sierra Crest. The Mana acted as middlemen in a trans-Sierra trade route that connected the Great Basin tribes, such as the Paiute, with the Yokuts of the Central Valley. The currency of this trade was often obsidian. There are no natural sources of obsidian, a volcanic glass prized for making razor-sharp arrowheads and tools, within the park's granite-dominated geology. The obsidian found in archaeological sites within Sequoia National Park has been chemically traced to volcanic sources on the eastern side of the mountains, such as the Coso volcanic field or the Mono craters. To bring this material west, traders had to carry heavy loads over high-altitude passes, such as Kearsarge Pass and Taboose Pass, often at elevations exceeding 11,000 feet. In exchange, the western tribes provided acorns, berries, shell beads sourced from the distant Pacific coast, and deer skins. This movement of goods proves that the High Sierra was not a wall, but a bridge connecting distinct cultural and ecological zones. Evidence of the spiritual and artistic life of these early inhabitants remains visible in the form of pictographs, rock paintings found on protected overhangs and cave entrances. At Hospital Rock, distinct red pigmented figures and abstract geometric shapes adorn the granite. The pigment was typically created from hematite, red ochre, mixed with a binder such as animal fat or plant fluids to ensure adhesion to the stone. The meaning of these symbols is a subject of anthropological study and respect for contemporary indigenous descendants. They may represent clan markers, maps of water sources, records of celestial events, or visions associated with ceremonial practices. Unlike petroglyphs, which are carved into the rock, pictographs are painted on the surface, making them more fragile and susceptible to weathering and vandalism. Their survival for centuries is a testament to the durability of the mineral pigments and the careful selection of sheltered sites by the artists. The most profound indigenous influence on the park's biology was the use of fire. Traditional ecological knowledge held that fire was a cleansing force. By setting low-intensity burns in the spring or late fall, the Monash kept the underbrush clear, which facilitated travel and reduced the ambush cover for predators. More importantly, these fires promoted the growth of useful plants. Deergrass, used for basket weaving, produces straighter, more flexible stalks after being burned. Berry patches produce more fruit when old woody growth is removed. This anthropogenic burning created a mosaic of habitats, preventing the forest from becoming a monoculture and maintaining the open, sunny floor that giant sequoia seedlings require for germination. When the U.S. government assumed control and implemented a policy of fire suppression, they unknowingly disrupted a management system that had been in place for centuries, leading to the dense, hazardous fuel loads that plague the forests today. Modern park management is now integrating this traditional knowledge, working with local tribes to reintroduce cultural burning practices as a method of ecological restoration. Moving from the human history to the atmospheric dynamics, the climate of Sequoia National Park is a study in vertical physics. The park sits within a Mediterranean climate zone, but its elevation creates a distinct hydrological engine. A critical phenomenon in the park is the quote, snow fence effect. As moisture-laden low-pressure systems sweep in from the Pacific Ocean, they hit the Sierra Nevada rampart. The air is forced upward, expanding and cooling. Because cold air holds less moisture than warm air, the water vapor condenses into snow. The zone of maximum precipitation usually occurs between 5,000 and 9,000 feet, precisely the elevation band where the giant sequoias grow. Above this altitude, the air has often been wrung dry, and the highest peaks can actually receive less snow than the mid-elevation forests. This specific band of heavy snow acts as an insulator. A deep snowpack keeps the soil temperature relatively constant, preventing the deep freeze that would damage the sequoia's shallow root systems. However, the nature of this precipitation is changing due to atmospheric rivers. These are long, narrow corridors of concentrated moisture in the atmosphere, sometimes referred to as the Pineapple Express when they originate near Hawaii. When a strong atmospheric river hits the Sierra, it can dump massive amounts of rain at high elevations that would normally see snow. This rain-on-snow event is physically destructive. The rain adds weight to the existing snowpack and melts it rapidly, sending sudden, massive pulses of water down the steep river canyons. These floods can rearrange the geomorphology of the riverbeds, tearing out riparian vegetation and moving boulders the size of cars. The Sequoia River, which has one of the steepest drops of any river in North America, is particularly flashy, meaning its water level can rise dramatically in a matter of hours during these events. Another atmospheric feature defining the park is the thermal inversion layer. In the summer, the San Joaquin Valley acts as a bowl, trapping heat and pollutants. Often, a layer of warm air sits on top of a layer of cooler air near the ground, preventing the air from mixing. This inversion layer caps the smog at a certain elevation. Visitors driving up the General's Highway often pass through a hazy brown band of air at around 4,000 feet before breaking out into the crystal-clear blue skies of the giant forest. Unfortunately, this smog layer coincides with the transition zone habitats, bathing the ponderosa and Jeffrey pines in ozone. Ozone is a potent oxidizer. It enters the stomata of the pine needles and damages the cellular structure, reducing the tree's ability to photosynthesize. This stress signal draws in bark beetles, creating a direct link between urban pollution and forest mortality. The seasonal rhythm of the park is governed by phenology, the timing of biological events. In the spring, the retreat of the snow line is the starting gun for life. The timing is critical. If the snow melts too early, the soil dries out before the peak solar radiation of summer, stressing the plants. If it melts too late, the growing season is shortened. One of the most spectacular phenological displays is the bloom of the Pacific dogwood. These understory trees do not produce petals. The large, creamy white flowers are actually modified leaves called bracts that surround a cluster of tiny, true flowers in the center. They evolved to be highly visible in the dappled shade of the sequoias to attract pollinators like beetles and flies. In the foothills, the timeline is accelerated. The California buckeye is the first to leaf out in late winter, and the first to drop its leaves in midsummer. This is a drought adaptation. The tree maximizes photosynthesis during the wet spring and goes dormant to avoid the desiccating heat of July and August. The fauna of the park operates within these climatic and botanical constraints, forming food webs of remarkable complexity. A standout species of the middle elevations is the fisher. The fisher is a mid-sized mustelid, a relative of the weasel and the wolverine, with a long, bushy tail and dark, lustrous fur. It is one of the few predators agile enough to hunt porcupines. The fisher has a unique method of attack. It circles the porcupine, darting in to bite at the quill-free face until the prey is subdued, then flips it over to access the vulnerable underbelly. Fishers are indicators of old-growth forest health because they require large, complex structures for denning. They do not excavate their own dens. Instead, they rely on cavities in large, living trees or hollow logs, features that are only found in forests that have been allowed to age for centuries. The fragmentation of forests by logging or severe fire threatens their population, as they are reluctant to cross open areas where they are vulnerable to predation by bobcats and coyotes. In the rocky alpine heights, a different drama plays out with the Sierra Nevada bighorn sheep. This subspecies is distinct from the desert bighorn found elsewhere in the American West. They are genetically adapted to the thin air and cold of the High Sierra. Their survival strategy is predicated on terrain. They live on the precipitous eastern slopes and high ridges where few predators can follow. Their hooves have a hard outer rim for digging into ice and a soft, rubbery inner pad that grips granite like a climbing shoe. The primary threat to the bighorn is not just gravity, but mountain lions. Interestingly, bighorn sheep populations in the park dropped dangerously low in the 20th century, partly due to diseases transmitted by domestic sheep grazing in the high country. Recovery efforts have been slow but steady. A fascinating ecological dynamic involves their relationship with high elevation. In winter, instead of migrating to the low foothills where food is abundant but predators are many, some herds choose to stay relatively high on windswept ridges where the snow is blown clear, trading easy calories for safety from cougars. The aquatic ecosystems of the park hide a tragedy and a hope involving the mountain yellow-legged frog. Historically, these frogs were so abundant in the High Sierra lakes that early explorers complained of stepping on them. They are unique among amphibians because their tadpoles take 2 to 4 years to metamorphosate into adults. This requires permanent bodies of water that do not freeze solid in winter or dry up in summer. The frogs overwinter underwater beneath the ice in a state of torpor. Their population collapsed due to 2 main factors: the introduction of non-native trout, which eat the tadpoles, and the arrival of the chytrid fungus. Chytridiomycosis is a disease that attacks the keratin in the frog's skin. Since frogs breathe and absorb electrolytes through their skin, the fungus effectively suffocates them and causes heart failure. Scientists in Sequoia National Park have been at the forefront of evolutionary rescue, identifying frogs that seem to have a natural resistance to the fungus and breeding them in captivity to repopulate lakes that have been cleared of non-native fish. Bird life in Sequoia offers a lesson in niche partitioning. The spotted owl is the silent watcher of the deep, multi-layered canopy. It is a perch-and-pounce predator, relying on stealth and surprise to capture flying squirrels and wood rats. Its large, dark eyes are adapted for the low light of the deep woods. However, it faces an existential threat from the barred owl, an invasive species from the eastern United States that has expanded its range westward. The barred owl is larger, more aggressive, and has a broader diet, outcompeting the spotted owl for territory and even hybridizing with it. This creates a management dilemma for the park: how to protect a native species when the threat is another native North American bird acting invasively. Conversely, the white-headed woodpecker is a specialist of the pine forests. Unlike other woodpeckers that drill deep into wood for larvae, The white-headed woodpecker uses its beak to pry open the scales of pine cones to extract seeds, and it gleans insects from the bark surface. Its striking black body and white head serve as camouflage against the high contrast pattern of sunlight and shadow on the tree trunks. The insect world of the park contains one of the most famous and misunderstood spectacles, the ladybug aggregation. In the transition zone, particularly in canyons like the converging tributaries of the Sequoia River, millions of convergent lady beetles gather in the cool months. They do not breed during this time. They are in diapause, a state of suspended animation similar to hibernation. They cluster together in masses that can cover entire logs or bushes, looking like spilled orange paint. This aggregation serves a thermal purpose, sharing body heat, and a defensive one. The combined scent of their defensive alkaloids deters predators. They migrate from the agricultural fields of the Central Valley up to the mountains to escape the summer heat and find a safe winter refuge, riding the wind currents to reach specific canyon sites used year after year. Deep underground, the biology of the caves is defined by endemism, species found nowhere else on Earth. The Sequoia cave systems are home to invertebrates that have evolved in total darkness for millennia. These animals, known as troglobites, often exhibit troglomorphy, the loss of eyes and pigmentation, and the elongation of sensory appendages like antennae or legs. In the Crystal Cave and others, scientists have identified unique species of pseudoscorpions, spiders, and millipedes. The energetics of this ecosystem are precarious. Without sunlight to drive photosynthesis, the food web relies on allochthonous input, nutrients brought in from the outside. This can be bat guano, debris washed in by underground streams, or even the shedding skin of other cave dwellers. A single footprint from a careless caver can destroy a mud bank that houses a microorganism community vital to this chain. The gray wolf, once absent from California for nearly a century, is a potential returning actor to the Sierra Nevada ecosystem. While established packs are currently further north, the vast wilderness of Sequoia represents potential habitat. The return of a top-tier canid would trigger a trophic cascade. Wolves hunt differently than mountain lions. They course their prey, testing the herd for weakness. This would alter the behavior of the mule deer, forcing them out of the open meadows and riparian areas where they currently graze comfortably, which in turn allows willows and aspens to regenerate, improving the habitat for nesting birds and beavers. This concept of the landscape of fear illustrates how the presence of a predator can increase the biodiversity of the vegetation. The scavengers of the park play a crucial role in nutrient recycling. The California condor, the largest land bird in North America with a wingspan of nearly 10 feet, historically soared over these mountains. They are obligate scavengers, feeding only on carrion. Lead poisoning from spent ammunition and carcasses drove them to the brink of extinction. While they are slowly being reintroduced in the region, they are occasional visitors to the park's high ridges. On the ground, the black bear acts as a primary decomposer accelerator. By tearing apart rotten logs to find grubs, they mechanically break down wood fiber, speeding up the return of carbon and nitrogen to the soil. Their digestive tracts also scarify seeds of plants like wild cherry and manzanita, increasing germination rates after the seeds are deposited in a pile of nutrient-rich fertilizer. The subalpine meadows are not just scenic expanses. They are battlegrounds for the ground squirrels and marmots. The yellow-bellied marmot lives in colonies in the rock piles, talus, bordering the meadows. They have a complex social structure and a system of alarm calls. A whistle can indicate an aerial predator like a golden eagle, sending the colony scrambling into the rocks, while a different chatter might indicate a terrestrial threat like a coyote. Marmots are true hibernators. They spend up to 8 months of the year underground, To survive this, they must double their body weight in the short summer. Their physiology during hibernation is a medical marvel. Their heart rate drops to a few beats per minute, and their body temperature nears freezing. They periodically arouse to sleep, a paradox, as hibernation is not sleep but a physiological suppression, and their brains need to warm up to perform the restorative functions of true sleep before cooling down again. Ecological disturbances in the park are often viewed negatively by humans, but are essential for renewal. Avalanches, for instance, are a geomorphic agent. In the high alpine, avalanche chutes are visible as vertical stripes of flexible vegetation, like willows and alders, cutting through the rigid conifer forest. These slide paths bring organic matter from the high peaks down to the valley floors. They also create open corridors that allow sunlight to reach the ground, supporting a diversity of sun-loving plants that cannot survive in the deep forest. This diversity attracts insects, which in turn attract birds and bears. Thus, the destructive force of the avalanche creates a corridor of life. The concept of refugia is becoming increasingly central to the park's scientific narrative. As the climate warms, species are moving upslope. However, the complex topography of Sequoia provides micro-refuges. A deep north-facing canyon may remain significantly cooler and moister than a south-facing slope just a few hundred yards away. These cool pockets may allow populations of plants and animals to persist, even as the regional climate becomes inhospitable. Identifying and protecting these potential climate refugia is a priority for conservationists, who map the landscape not just by current inhabitants, but by future potential. Water quality in the park serves as a barometer for the entire region. The lakes of the High Sierra are ultra-oligotrophic, meaning they are extremely low in nutrients and biological productivity. This makes them exceptionally clear. However, they are highly sensitive to nitrogen deposition. Exhaust from automobiles and agriculture in the Central Valley contains nitrogen compounds that drift up into the mountains and fall as acid rain or dry particulate. This added nitrogen acts as a fertilizer, changing the algal communities in the high lakes. The shift from a diatom-dominated community to one dominated by other algae types alters the food base for the zooplankton, which feeds the insects and frogs. This invisible chemical alteration connects the morning commute in Los Angeles or Fresno directly to the pristine waters of the High Sierra wilderness. The interconnectedness of the giant forest ecosystem extends to the canopy soil. Recent research has revealed that in the crotches of the massive limbs of the giant sequoias, hundreds of feet in the air, soil accumulates. This soil is formed from the decomposition of millennia of needles, bark, and cones. In this arboreal soil, scientists have found earthworms, insects, and even ferns growing, creating a hanging garden ecosystem completely detached from the ground. This discovery shattered the assumption that the biological activity of the forest was confined to the forest floor. It suggests that the canopy of a giant sequoia is not just a collection of branches, but a vertical archipelago of habitats, each supporting a micro-community that we are only beginning to understand. Even the granite itself has a biological component. On the exposed peaks, crustose lichens paint the rock in shades of neon green, orange, and black. Lichen is a symbiotic organism, a partnership between a fungus and an alga, or cyanobacteria. The fungus provides the structure and protection from UV radiation, while the alga provides the food through photosynthesis. These lichens produce acids that slowly dissolve the minerals in the rock, beginning the process of soil formation on the molecular level. They are the pioneers, the first responders of the biological world, preparing the sterile stone for the eventual arrival of mosses, grasses, and finally, the great forests. This slow, microscopic erosion is the counterforce to the tectonic uplift, a silent war between biology and geology that has continued for epochs. In the end, the specific details of Sequoia National Park, the chemical warfare of the acorn, the thermal physics of the ladybug swarm, the hydraulic engineering of the sequoia, and the hibernation physiology of the marmot, reveal a landscape of immense intricacy. It is a place where the cultural memory of the monarchy is etched into the bedrock, and the future of the ecosystem is written in the chemistry of the atmosphere. The park is a continuous dialogue between the living and the non-living, a testament to the diverse strategies life employs to survive in a land of granite giants. To understand the true magnitude of Sequoia National Park, one must look beneath the veneer of the living forest and penetrate the hard, silent history of the stone itself, for the biological grandeur of the surface is merely a recent decoration upon a geological architecture of immense age and violence. While the previous explorations of the park focused on the interactions of flora, fauna, and human history, the foundational reality of this landscape lies in the deep time of the Earth's crust, a story not of centuries or millennia, but of epochs that stretch back hundreds of millions of years. This geological narrative provides the stage upon which the drama of the giant sequoias is enacted, and to comprehend the park, one must comprehend the titanic forces that built the Sierra Nevada. The story begins in the Paleozoic era, long before the first dinosaur walked the earth, when the western edge of the North American continent was not where it is today, but situated hundreds of miles to the east. The land that would become Sequoia National Park was then a submerged continental shelf, a shallow, warm sea teeming with primitive marine life. Sediments from the continental landmass washed into this sea, creating layers of sand, silt, and mud, while the calcium-rich shells of dying marine organisms accumulated on the seafloor to form thick beds of limestone. These sedimentary layers were the raw material for the first chapter of the park's history. Over hundreds of millions of years, these layers were buried and subjected to the immense heat and pressure of tectonic collisions, transforming them into metamorphic rocks. The sandstone became quartzite, the shale became slate or schist, and the limestone recrystallized into marble. These ancient metamorphic rocks, often referred to as country rock by geologists, are the oldest physical entities in the park, yet they are largely invisible to the casual observer, hidden or eroded away, existing now only as roof pendants, isolated patches of dark rock perched atop the younger, lighter granite peaks, like the tattered shingles of a roof that has mostly collapsed. The defining event in the geological birth of Sequoia National Park occurred during the Mesozoic era, roughly 100 million years ago, with the subduction of the Farallon Plate. This massive oceanic tectonic plate was moving eastward, colliding with and sliding beneath the westward-moving North American continental plate. As the water-laden oceanic crust descended into the hot mantle, the water was released, lowering the melting point of the surrounding rock and generating vast plumes of magma. This molten rock, being less dense than the surrounding solid rock, rose buoyantly through the crust. However, unlike the magma that fuels the volcanoes of the Cascade Range or Hawaii, this magma did not breach the surface. Instead, it stalled miles underground, pooling in massive subterranean chambers known as plutons. It was in these dark, pressurized, superheated chambers that the Sierra Nevada batholith was born. The term batholith is derived from the Greek words for deep and rock, and it describes a massive amalgamation of these individual plutons that have coalesced into a single granitic spine. The formation of the granite was a process of slow, deliberate cooling. Because the magma was insulated by miles of overlying rock, it lost its heat over hundreds of thousands of years. This slow cooling allowed the chemical elements within the melt to organize themselves into large, visible crystals. The minerals that crystallized first, hornblende and biotite, formed dark specks. Then came the plagioclase feldspar, followed by potassium feldspar and quartz. The interlocking of these crystals gave the granite its immense strength and its speckled salt and pepper appearance. The granite of Sequoia National Park is not uniform. It is a complex mosaic of these different plutons, representing different pulses of magmatism over millions of years. For example, the giant forest sits atop the giant forest granodiorite, a rock slightly richer in iron and magnesium than true granite, giving it a slightly darker hue. In contrast, the high peaks around Mount Whitney are composed of the Whitney granodiorite. Geologists can map the boundaries between these plutons, reading the subtle shifts in mineral composition and texture as a record of the shifting thermal dynamics of the ancient magma chamber. The presence of large phenocrysts, rectangular crystals of potassium feldspar that can be several inches long in some of these rocks, indicates periods of extremely slow cooling, where these minerals had ample time to grow before the rest of the melt solidified around them. For millions of years, this massive granite block lay buried deep within the crust. The landscape above it was likely a chain of volcanoes, similar to the modern Andes Mountains, fed by the magma chambers below. However, the erosional forces of wind and water slowly stripped away the overlying volcanic and metamorphic rock, acting like a scouring pad, removing the layers of a painting to reveal the canvas beneath. By the time of the Cenozoic era, much of the granite had been unroofed, brought closer to the surface by the relentless removal of the material above it. Yet the Sierra Nevada as a high mountain range did not yet exist. The region was likely a series of low, rolling hills, with rivers flowing sluggishly toward the Pacific. The dramatic uplift that created the modern topography began relatively recently in geological terms, perhaps fewer than 10 million years ago, and accelerated significantly in the last few million years. The precise mechanism of this uplift is a subject of ongoing scientific debate, but it is generally linked to the crustal extension that created the Basin and Range province to the east. As the crust stretched and thinned, the rigid block of the Sierra Nevada was tilted. The fault zone on the eastern edge of the range acted as a hinge. The eastern side was thrust upward, creating the steep, imposing escarpment that faces the Owens Valley, while the western slope, the side containing Sequoia National Park, tilted gently downward, creating the long, ramp-like gradient that rises from the Central Valley. This tilting had a profound effect on the hydrology and geomorphology of the park. As the gradient of the western slope increased, the rivers that flowed down it gained kinetic energy. The Kaweah, Kern, and Kings rivers, which had previously meandered through low hills, suddenly became powerful excavators. They began to slice downward into the granite, carving the deep V-shaped canyons that define the lower elevations of the park today. This process of fluvial incision was rapid and aggressive, cutting through the hard rock and creating the steep canyon walls that isolate the different sequoia groves. The Kern River, in particular, took advantage of a pre-existing weakness in the crust, the Proto-Kern Canyon Fault, to carve its remarkably straight, deep north-south trench, a feature that stands in contrast to the generally east-west orientation of the other drainage systems. While the rivers carved the valleys, the details of the landscape were refined by a process known as exfoliation or sheeting. This is a mechanical weathering process specific to massive bodies of rock like granite plutons. The granite formed under immense pressure, kilometers beneath the surface. As the overlying rock was eroded away, that pressure was released. In response, the granite expanded slightly, much like a compressed sponge springing back when a weight is removed. However, rock is brittle. It cannot stretch. Instead, the expansion caused fractures to form parallel to the surface of the rock. Over time, gravity and water worked to peel off these outer layers in curved slabs, creating the distinctive dome shapes seen in Moro rock and beetle rock. This process is continuous and ongoing. The fresh, white scars seen on granite faces today are evidence of recent rockfalls where exfoliation slabs have detached and plummeted to the talus slopes below, creating Seine Tate. The final and most dramatic sculpting of the park occurred during the Pleistocene epoch, often called the Ice Age. Starting roughly 2.5 million years ago, the global climate cooled, and the High Sierra became a generation point for massive glaciers. These were not merely patches of ice, but rivers of ice thousands of feet deep. The accumulation of snow in the high cirques, bowl-shaped depressions near the peaks, compressed into ice, which then flowed downhill under its own weight. The glaciers acted as powerful abrasive agents. Rocks embedded in the bottom of the ice scraped against the bedrock, acting like sandpaper to polish the granite surfaces to a glass-like smoothness that can still be felt today. This glacial polish is often preserved on high-altitude slabs, reflecting the sunlight in a blinding glare. The glaciers transformed the landscape. They took the winding V-shaped river valleys and plowed them into straight, wide, U-shaped troughs. The Tokapa Valley is a prime example of this glacial architecture, with its flat floor and towering vertical walls. As the main glaciers flowed down the major canyons, smaller tributary glaciers flowed in from the sides. Because the main glacier was much deeper and heavier, it cut its valley deeper than the tributary glaciers could. When the ice melted, the tributary valleys were left hanging high above the main valley floor. These hanging valleys are now marked by spectacular waterfalls, such as Tokapa Falls, where the water plummets from the lip of the hanging valley to the floor of the main canyon. The glaciers also transported immense quantities of rock. When the ice melted, it dropped this debris in ridges known as moraines. Lateral moraines mark the sides of the glacier's path, while terminal moraines mark the furthest point of the glacier's advance. These piles of unsorted rocks and sediment often acted as natural dams, blocking streams and creating the beautiful alpine lakes that dot the high country. The lakes of Sequoia National Park, such as Pear Lake and Precipice Lake, are essentially glacial footprints, water filling the depressions gouged out by the ice or dammed by its debris. One of the most scientifically significant aspects of the park's geology is the presence of karst topography and caves. While granite dominates, the ancient roof pendants contain bands of marble. Marble, being composed of calcite, calcium carbonate, is soluble in acidic water. Rainwater absorbs carbon dioxide from the atmosphere and from decaying organic matter in the soil, forming a weak carbonic acid. When this acidic water seeps into fractures in the marble, it dissolves the rock, enlarging the cracks into tunnels and chambers. This process has created a subterranean world beneath the park that is as complex as the forest above. Sequoia National Park protects over 200 caves, making it one of the most cave-rich areas in the western United States. These caves are not merely geological oddities. They are repositories of paleoclimatic and paleontological data. The speleothems, stalactites, stalagmites, and flowstones grow by the slow deposition of mineral-rich water. As they grow, they trap trace elements and isotopes of oxygen and carbon. By analyzing the rings of a cross-section stalagmite, similar to analyzing tree rings, scientists can reconstruct the climate history of the region over tens of thousands of years. These mineral archives reveal periods of drought and glaciation, providing a precise timeline of the varying climates the Sierra Nevada has experienced. Furthermore, the caves serve as paleontological treasure chests. The stable temperature and humidity inside the caves create an ideal environment for the preservation of bone. Animals that fell into vertical shafts or used the caves as dens died and were buried in the sediment. Excavations in the park's caves have yielded fossils of Pleistocene megafauna that paint a picture of a very different ecosystem. Paleontologists have found the remains of the short-faced bear, a predator larger and more long-legged than the modern grizzly, capable of running down horses. They have found the bones of the dire wolf, the noble marten, and extinct species of horses and camels. These discoveries prove that the High Sierra was once home to a savanna-like fauna that migrated up and down the slopes, much like the modern deer herds. The Mineral King area of the park offers a particularly rich window into the pre-granite history. Here, the roof pendants are thick and complex. The rocks at Mineral King include metavolcanics, ancient lava flows and ash beds that have been metamorphosed, and metasediments that preserve the ripple marks of ancient shorelines. This area was the site of intense mining interest in the late 19th century, as the contact zones between the granite and the metamorphic rock are often rich in mineral ores. The heat of the intruding magma caused chemical reactions in the surrounding country rock, concentrating elements like silver, gold, and zinc. The name Mineral King reflects the optimism of these early prospectors, although the geology ultimately proved too complex and the ore too scattered for profitable industrial extraction, saving the valley from large-scale destruction and eventually allowing it to be added to the national park. The relationship between the geology and the modern ecosystem is intimate and causal. The mineral composition of the granite directly dictates the chemistry of the soil. Sierra granite is composed largely of silica and aluminum silicates, which weather into soils that are acidic and poor in essential nutrients like calcium and phosphorus. The plants of the park have had to adapt to this nutritional scarcity. The giant sequoia, for instance, requires well-drained soil, which the coarse, sandy soil derived from disintegrating granite, known as grue, provides perfectly. However, the lack of nutrients means the trees must be efficient recyclers. This is why the forest floor is so important. The slow decomposition of needles and branches releases the locked-up nutrients back to the trees. The symbiotic relationship with mycorrhizal fungi is an adaptation to this geological reality. The fungi are better at extracting phosphorus from the mineral grains than the tree roots are, trading this mineral wealth for sugars. In the areas where marble roof pendants weather into soil, the ecology shifts. The soil here is less acidic and richer in calcium. This allows for the growth of different plant communities, including rare species that are calciphiles or calcium lovers. These botanical islands within the granite sea are hotspots of biodiversity. The marble stripe in the park supports unique assemblages of plants that cannot survive on the surrounding granite terrain. Thus, a map of the park's geology is also a predictive map of its botany. The hydrological cycle of the park is also fundamentally shaped by the rock. Granite is generally impermeable. Water cannot flow through the rock itself. However, the Sierra granite is heavily fractured. These joint systems, the vertical and horizontal cracks in the rock, act as a plumbing system. Snowmelt percolates down into these fractures, filling the deep reservoirs of the rock. This hard rock aquifer is critical for the survival of the forests during the dry summer months. As the surface soil dries out, the trees tap into the water stored deep in the fractures. In some places, this water travels deep enough to be heated by the Earth's geothermal gradient or by residual heat from deep crustal processes, returning to the surface as hot springs, such as those found along the Kern River. The geological stability of the park is a relative concept. While the granite seems eternal, the landscape is in a constant state of adjustment. The Sierra Nevada is a seismically active region. The same faulting forces that uplifted the range continue to operate. Small earthquakes are frequent, relieving the stress that builds up in the crust. These tremors can trigger rockfalls, which are the primary agent of erosion today. A single rockfall event can reshape a canyon wall, alter the course of a stream, and create new habitats. The talus slopes, the aprons of broken rock at the base of cliffs, are the product of this continuous shedding. These slopes provide the labyrinthine homes for pikas and marmots, creatures that rely on the geological debris for protection. The study of the park's landscape also involves the investigation of, quote, paleosurfaces. These are remnants of the ancient, gently rolling landscape that existed before the uplift and incision of the canyons. The high plateaus, like the Chigupa Plateau and the Boreal Plateau, are thought to be fragments of this ancient topography, preserved at high elevation. These flat areas are unique ecological zones, often supporting subalpine meadows and forests that differ significantly from the steep slopes that surround them. They are geological ghosts, flat lands hoisted into the sky, preserving the shape of a world that no longer exists at lower elevations. The impact of the Little Ice Age, a period of global cooling from roughly the 14th to the 19th century, is also written in the landscape. While the massive Pleistocene glaciers had long since retreated, the Little Ice Age saw the formation of small cirque glaciers, or glacierets, in the highest, most shaded pockets of the High Sierra. These small bodies of ice, such as the Lilliput Glacier, are the last living remnants of the glacial history of the park. They are currently in rapid retreat due to anthropogenic climate change, and their disappearance will mark the end of an active geological process, glaciation, that has shaped the park for millions of years. The loss of these glaciers also alters the late summer hydrology, as they provide a cool, steady trickle of water to the alpine streams when all other snow has melted. The interaction between fire and geology is a subtle but important dynamic. High-intensity fires can cause spalling of the granite. The intense heat causes the outer layer of the rock to expand rapidly and flake off. While this happens on a smaller scale than the tectonic exfoliation, cumulatively, over thousands of years of fire history, it contributes to the weathering of the boulders and outcrops in the forest. Furthermore, the ash from fires is one of the few ways that nutrients are rapidly mineralized and returned to the soil, briefly overcoming the nutrient limitations imposed by the granitic parent material. The geological history of Sequoia National Park is also a history of discovery. The first geological survey of California, led by Josiah Whitney in the 1860s, struggled to comprehend the verticality of the terrain. They mapped the peaks and named the mountains, but the mechanisms of uplift and glaciation were still poorly understood. John Muir, who explored the range extensively, was one of the first to correctly identify the role of glaciers in shaping the Yosemite and Sequoia landscapes, a theory that was controversial at the time but has since been vindicated. Muir recognized that the polish on the rocks, the erratic boulders, and the shape of the canyons could only be the work of ice. His observations bridged the gap between the aesthetic appreciation of the landscape and the scientific understanding of its formation. The fossil record within the park's metamorphic rocks provides a connection to the global history of life. The marine fossils found in the Mineral King roof pendants, ammonites, crinoids, and bivalves, link the High Sierra to the Mesozoic oceans. These creatures lived and died in a tropical sea, yet their fossilized remains now sit at 10,000 feet above sea level, encased in rock that has been cooked and squeezed by tectonic forces. This juxtaposition is a powerful illustration of the dynamic nature of the Earth's crust. It forces the realization that the mountains are not static monuments, but are the temporary result of forces that recycle the planet's surface. The floor of the ocean becomes the roof of the continent, and given enough time, erosion will wash it all back to the sea to begin the cycle again. The specific mineralogy of the contact zones, where the hot granitic magma met the cool country rock, creates rare minerals that attract collectors and scientists. Skarn deposits formed in these contact aureoles contain garnet, epidote, and tungsten-bearing minerals like scheelite. These minerals are the product of fluid exchange between the magma and the host rock. The superheated fluids, rich in silica and metals, invaded the limestone or shale, reacting to form these new, often colorful crystal structures. While mining is prohibited in the park, these mineralogical distinctiveness adds another layer to the scientific value of the landscape. In the deep canyons, the power of water as a geological force is visible in the potholes drilled into the granite bedrock. These are not formed by the water itself, but by the tools the water carries: sand and gravel. A stone gets caught in a depression in the bedrock, and the swirling current spins it around, drilling a perfectly circular hole into the solid granite. Over time, these potholes can grow to be several feet wide and deep, sometimes merging to form complex sculpted channels. This process is a microcosm of the larger canyon cutting, a demonstration of how the soft fluid of water, armed with the hard grit of the earth, can conquer the hardest stone. The geological story of Sequoia National Park is, therefore, a composite narrative. It is the story of the slow accumulation of sediments, the violent collision of plates, the hidden cooling of magma, the catastrophic uplift of mountains, the grinding power of ice, and the patient dissolution of limestone. It is a story where the characters are minerals and the plot points are measured in millions of years. This geological foundation determines everything that lives upon it. The height of the mountains determines the weather. The composition of the rock determines the soil. The fracture patterns determine the water availability. The giant sequoia, the black bear, and the human visitor are all, in a profound sense, guests of the granite. The park is a display of the Earth's anatomy, laid bare by erosion for us to study, offering a glimpse into the deep processes that build and destroy continents.